Of course.
All right. Hello, everyone. We're getting started. We're finishing up nutrition label or labeling lecture and starting data analysis. So again, to just read some recap questions to get us to remind us what we were talking about last time. Is nutrition labeling required for all food? Okay, hold on. I need to fix something before I continue. I need to share my screen and sure that this projects. Okay. And this is recording. All right, I just want to double check. All right. So is nutrition labeling required for all food? Gretchen? No. Can you give me a specific example of when it's not required?
Poultry, meat, small packages.
Small packages within a big package, produce. So there are exemptions for nutrition labeling, but in general, it's required. It's not an optional unless in these specific cases. What agencies regulate nutrition labeling? Yes, Sandy?
The FDA and
FDA, FDA for everything except the meat, poultry, and eggs, which are regulated by the Food Safety and Inspection Services. Okay, what type of analytical methods are required to obtain the values listed on the nutrition label? This is a common question that I like, and you might see it in a quiz. When I say what type, I'm not asking for a specific method, category of methods. Radhika? Official method of analysis. So that is what I mean when I say what type. It kind of throws students off sometimes, like, what am I asking? Type of a method, specific method? No, I'm asking about a category. Official methods of analysis for nutrition labeling. These that were verified by organization, official organizations that verified the method, like AOAC, AOCS, AACCI. So these are official organizations that that kind of validate methods. So they should be primary methods. So remember the term. Primary methods, official methods, reference methods. So these mean they're the same thing. Secondary methods are methods that are fast methods that are based or calibrated based on primary methods. That's why they're called secondary methods. So we cannot use secondary methods for nutrition labeling. What are new changes in the nutrition label? Okay, Preston.
Serving size, calorie content.
They bolded serving size and calorie. They added vitamin D and potassium. True.
Since they added that, they had to remove 2 and they removed
Vitamin A and C not on the salad.
They added the additives.
They added sugar, Zoe.
They took off calories from that.
They took off calories from fat. Elizabeth, did she take your answer?
Yeah.
But she just plus 2 another number. Okay. When can you claim calorie free? I know I told you you don't have to remember these values, but this, for example, is nice to remember, Michael.
Less than 5.
Yes. Less than 5 calories, you can claim calorie free or 0 calories because it's rounded to 0. I know I told you you don't have to learn rounding rules. It's just FYI. You won't see that in a test, huh?
Why 5? Typically you do 0 to 4. You round down.
I don't know why they choose 5. Anything less than 5, they said you can claim. That's regulation.
So, and when they use 6, I'm guessing they round up to 10 to make it easier. All right. Yeah, you claim 6
You
down.
know, life is not perfect, Drew. We just have to live with it.
It's dumb.
Yeah. Tell me about it. Okay, so the grade question we didn't get to yet. That's where we stopped last time. Why is this not going? Come on. No? All right. Compliance. So you have to be in compliance when you do nutrition labeling. So we have to follow rules of sample collection. Chapter 5, we're going to talk about sampling and specifically sample collection for nutrition labeling. So we'll talk more about that under chapter 5. Method of analysis, official method of analysis, specifically FDA requires AOAC methods unless a specific method is specified in the Code of Federal Regulation. FSIS, USDA Analytical Chemistry Laboratory Guidebook, or they would say, if not that, AOAC methods are also accepted. So now level of compliance. Now this last time I joked with you in terms of what you need to know. These you need to know for real. God, trust me on that. So, but it's not hard to remember these values. You want to remember anything that is added, like you added calcium or you added vitamin B12 or you added vitamin D. Whatever you add, you have to label it at least 100% or more of what you have in there. So if it is less than 100%, you are not in compliance. So I'll give you an example. So for vitamin C, when on the old label, it would have to be reported. And the value there has to be, because if you add vitamin C to orange juice or any other type of beverage, you have to have at least 100% of what you claim is present regarding percent daily value. So manufacturer make sure they add more vitamin C than what they claim, because during storage, vitamin C degrade. During processing, it might degrade. During storage, it might degrade. So they make sure that they have extra so that they never fall under the compliance level for an added nutrient. Okay. So for other nutrients that are endogenous, that means already present, you didn't add them, you can have 80% or higher. So it can be less than 100 in this case. So you are still within compliance if it's 80% or higher. So these two values you just have to remember. And the other one that is important to remember, it's for calories, fat, sugar, saturated fat, cholesterol, sodium, those that might have adverse effect if you have them in excess, right? So you cannot claim, or you cannot have more than 120% of what you claim. Let's say you have 10 grams of fat, but when they come and measure and they find that you have 13 grams of fat, that's more than 120% of what you said you have of fat. So that is, you are not within compliance. Okay. So that, yes, Brittany?
So does that mean if you, like, for example, if you're eating a packet of cookies that claims to have 100 calories, it could have up to 100 calories or 120 calories?
It could have up to 120 calories. You're still within compliance if the label says 100. But if they measured calories for you in an audit and it was 130, you're not in compliance. Absolutely. Now, Drew, why? I don't know. This is the rule. Don't get hired by the change the rounding. All right, so the other thing on nutrition label that you would see is nutrition claims, okay, or health claims. So, no, before health claims, content claims, sorry, I'm ahead of myself. Content claims. So if you want to claim low fat or reduced fat, you have to have a specific level below the reference in order for you to say low or reduced, light, free, high, a good source of. You have to have a specific amount compared to a reference. So this table, for some reason, was removed from the new edition of the book, but you find it in an older edition of the book. It's a good reference. Here, you don't have to remember any of that, but it's a good reference because there is, I think, 1 or 2 questions in your lab report for nutrition label. Like, what can you claim? Can you claim a good source of calcium? On what basis you can make that claim? So this kind of table tells you when you can claim calorie free, less than 5 calories. I didn't make that rule. Low, 40 calories or less. Reduced, 25% fewer than the reference amount or the product that was not reduced in calories. So, and this goes on for other nutrients, for total fat, for saturated fat, for cholesterol, for sodium, and for sugars. And there is also a table specific for a good source of, a high source of. That would be a good reference for you in the future to understand when you can claim something, a content-related claim. Okay, so now the last one here is health claim. So you can have specific health claims that are approved by the FDA. So how do they approve health claims? It takes a long time and a lot of human-based research to approve a specific claim. So any nutrient that is related to a health, whether in an adverse way or a positive way, it has to be proven by a lot of human studies over the years. So there are so many different health claims, and these are among some of them. So calcium has been related to osteoporosis. So a high source of calcium would be good for osteoporosis, dietary fat, and cancer. Sodium and hypertension, fruit, vegetables, and cancer. Folate, neutral tube defects, neural for babies. Sugar, alcohols, and dental caries. So these are some of the health claims. There's also there are others related to dietary fiber. For example, soy protein, there is claim for that. So there are different claims, and these are just examples of these claims. Yes, Abby?
Also claiming for the ingredients to be added in the composition or to be limited.
The nutrients, when they add?
To be added, we are claiming for the nutrients to be added.
Not for the nutrient claim. For nutrient claim, it can be added or it can be naturally present. So if you're making a claim for sodium, you should have, let's say, if you have a product that has the regular amount of sodium due to formulation, has a certain amount of salt, but you produce the same product with a reduced amount of salt, it has to be reduced by a certain amount in order to claim as low or reduced. Does that make sense? Is that your question?
Yeah, but does that contradict with the health claim?
Health claim is completely different. Health claim is if you have a good source of calcium, then you can put a health claim on there, not just a good source of calcium, you can put calcium and osteoporosis claim. Yeah. You can say like, this is good, this product is high in calcium, is good for osteoporosis. You can put that on your claim. That's different from just saying a good source of or an excellent source of. Okay. All right, so that ends nutrition labeling lecture. And from there, I just want to make sure I'm recording. Last time, for some reason, it stopped recording. Okay. It's recording still, good. Let's see. Data analysis. Well, evaluation and of analytical data. So this is chapter 4 in your book. This you're going to, yes. Oh, didn't you tell me you want to say something about Food Science Club
Sure, I can do that
at the end?
Or
I just remembered.
Okay, no worries. I'll be really quick. So my name is Paige Benson. I am the president of our Food Science and Nutrition Club. We also have some other leaders from the team this year. We have Sandy, we have Nigel in the back. We have Miss Gretchen right here. But anyways, we have a lot of events coming for this semester. If you're not on our email blast, feel free to write down your email. You can email me, you can stop me right after class. And you can give me your email to be a part of like our email blast for the semester, see all the events that are going on. And yeah, so if you're interested, come find me or anything. Yes, today is our first meeting at 5 p.m. in the FSM building.
Yeah, I'm just gonna put a spiel, encourage you guys to participate. It's a lot of visibility, especially your seniors. There are a lot of meetings where you see industries. A lot of students get industry internships or even positions by just networking. A lot of social activities, a lot of product development, competition activities, games. So it's really to get to know each other outside of the classroom, and to also would look good on your resume if you want to apply for scholarship. Being part of FSM Club helps, especially in IFT scholarship, for example. They look not just at your academics, they look at the extracurricular involvement that you have. So please reach out to Paige. Good. So Paige, you had a question now.
Yeah, how much scientific research has to be done for those specific health claims?
Oh boy, I don't know how much to give you a number, but a lot, and usually it takes years. So it does take a lot of validation before they can say, yes, this is true. Because with the human research, there's a lot of variability. And if you just take 1 or 2 studies that shows positive results, you're going to see another study that shows negative results. So it has to be probably, I want to throw out a number, more than 90% of the studies should give you a positive link for the FDA to approve such claim. Yeah. Yes, Alisa.
Is it different for supplements though?
For supplements?
Yeah, for like nutritional supplements.
So can you give me an example so that I understand your question?
Like, let's say there's an herb that you would think like, oh, reduces your fat levels, right?
Oh, you can't put a claim on your label without FDA approving that. That would be illegal just to put a claim based on few studies that has not been approved through the regulatory channels. It has to be FDA or FSCIS, depending on the type of food product. So you cannot just claim something on your own. So Cheerios, for example, they have the heart on that just because of the high fiber amount. So there is a correlation with fiber and heart health, right? Or low cholesterol and heart health. So you can do these claims, but anything like, oh, a herb has been found, blah, 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 by a couple of studies, you cannot just put that on your nutrition label, at least not in this country. Tyler?
I thought that was going to cover supplements.
I tell you, you're very well protected with your N95.
I was just wondering, I thought supplements weren't covered by FDA.
Supplements?
Yeah,
No,
like-
not like what kind of supplements? If we're talking minerals and vitamins, yes. If we're talking CBD, I'm not quite sure. Is CBD approved by FDA? Not yet. I don't think so. I mean, with supplements is different than foods, right? So the apply to the food product is different than what applied to, like, if you're selling CBD oil, it's a different category of approvals. And I'm not an expert, so I'm not going to speak much to that. Okay. And I won't test you on that either. So, Yeah, my middle name is Pamela, legally. So, what's my first name? He won't get +2 for that question. So just let you know. I'll have a half an hour where you can practice my first name because it's difficult to pronounce after class.
Okay.
That's not going to be on the test. All right, so we're going to evaluate data throughout the semester. So this is kind of an introductory kind of lecture. You've gone through data evaluation in your high school, potentially looking at mean, standard deviation, coefficient of variation. You've done that in math at some point. So this is just a refresher and how it relates to your food data that you're going to produce throughout the semester. Okay, so I want to remind you again of precision and accuracy. There will be a lot about precision and accuracy throughout the semester with regard to the methods, with regard to the data you generate. So let's look at this one. Method A is more precise in measuring glucose content than method B. See shots 3. A and C. I will hear what Dara has to say. Just A. Michael. Drew doesn't need extra credit for now, but go ahead. No,
Just A. Okay.
I'm just teasing you.
I know you are. It just came out of nowhere. I wasn't expecting it.
What is it now? A?
It's just A.
It's just A. So, Shri, you're right with A. C has to do with accuracy. So when you're closer to the true value or a reported value, then that's your value is more accurate. When you have standard deviation is related to your measurements of the same sample, the multiple measurements of the same sample and how close it is to each other. The closer the values are, the lower is your standard deviation. So it's only A. Just making sure I didn't miss anything. Okay, so very simple. Like I said last time, or I don't know when I said it, when you do an experiment, you don't run it once. Okay, so you have to have multiple times that you run your analysis. So we call that replication. So, and then the more intense the method is, the more steps you have in your method, the more error that you can incorporate. So the more replications would be better to reduce your error. So then you have to do replicate analysis. Basically, long story short, you have to do replication. And in order to evaluate your accuracy and precision, you start by calculating the mean, the average. Sometimes you look at the median, but for not a lot in food analysis, we care about the median in the test. So when you do a test and I give you the stats, I'll tell you the median so that you know where you stand. But in general, for data such as the data we generate, we care mostly about the mean, the average. Okay, and then we test reliability of this data. So we test it by determining accuracy and precision. And the errors are important because the errors we make contribute to our precision and accuracy. So the more error you incorporate, the lower is your precision and potentially the lower is your accuracy. We talked about specificity last time. Specificity is how specific your assay is to the component you're measuring. We gave the example last time, are we measuring total carbohydrate or are we measuring glucose? So how specific your assay is. And then there is sensitivity and detection rate. I just remembered an example for specificity where sometimes your assay might pick up all of the carbohydrate in the juice, including fiber that comes from the package. So that can skew your results. So if you use a tube that comes out of a package and it still has some carbon chips in it, like carton, chips in it, and then you don't wash it, rinse it before you use it, and then you're determining glucose. So your assay has sulfuric acid that is going to hydrolyze all of your carbohydrates that coming from the sample and coming from contaminations. Then you end up having a spike in your assay. So if you're after measuring glucose and you use a general assay, you will end up being hurt with the specificity of that assay. Okay, sensitivity and detection limit. This is Huxley also can be referred to as threshold. So you might hear that term threshold. So basically how low of a value you can get that you can trust and it is not noise. We'll talk about instrument noise when we cover instrument analysis in spectroscopy, for example. So how well the assay can differentiate between values or how low of a difference this method can detect. So can there be a difference of 0.1 micromole that you can detect, or is it 0.1 nanomole that you can detect the difference between one sample or another? So that it has to do with detection limit, threshold, sensitivity. So this has, these are all related to how sensitive the analysis is. Okay, a lot of the time you're going to fit a standard curve because you're going to have standards, you're going to do calibration, and you're going to detect concentration in a set of unknowns. So a lot of the time you are doing linear regression. So we get standards, we prepare standards in known concentration, and let's say it's an absorbance assay, we measure absorption. Or it's an HPLC assay, we measure area under the curve. Then you would have area under the curve, let's say, as a y-axis, and as x-axis is the known concentration. And you plot a linear regression. And you get equation of the line, which you use to predict the concentration of your unknown by measuring the area under the curve of that particular compound in the unknown sample. So we're going to do a lot of that in the entire semester. We're going to learn about correlation coefficient, how well the data fits a straight line, or how well the two variables are correlated, positively or negatively correlated to each other. That's correlation coefficient. You'll hear also coefficient of determination, which is R squared. How well the equation of the line predicts your concentration. So the prediction power of that equation is by R squared. So all of this you're familiar with, you've done math, you're doing potentially stats, or you've done stats. So this is just putting things in perspective with regarding to food analysis. Reporting results, this is an important concept. So, you have a calculator, you multiply two numbers, and you get, if you have decimal points, you get infinite number of decimal points. And then students put them in a table, and they put 10 decimal points after the numbers. Like, do we really need all of these? No, we have to look at first the sensitivity, the accuracy of the instruments or the balance we're using. And according to that, we select our significant figures. So we have significant figures that are related to the accuracy of the tools we're using, the pipettes we're using, the burettes we're using, the volumetric flask we're using, whatever we're using. We can go to how accurate they are to how many decimal points, and that will dictate our significant figures. We'll talk about that too. And there's also rejecting data. Sometimes you have, let's say, 4 replication. And this will be true for the caffeine lab, where one group will do 2 reps, another group will do another 2 reps, and then you combine the data and you have 4 replication. You look at your data and you see that one of them is completely out. It's looking very different than the other 3. If you include it in the calculation, your CV, coefficient of variation, is going to be trashed. Your accuracy will be trashed. So you cannot just say, okay, I don't like this data point, I'm going to throw it out. There is a statistic measure to reject that data point. So we'll talk about that, and it's called Q-test. So we'll talk about how you would reject the data if it's skewed so that you improve your precision, you improve your accuracy. All right, so now it's time to just do some of the easy exercises for everybody to get +2. So pull out a piece of paper and then solve on that piece of paper and then give it to me before you leave. So here we go. Just practice calculating the mean. If you have an answer, you can tell me. The mean. Yeah, that was quick. What about your median? Yeah, there you go. Make sure you have it on your piece of paper so that you can get your credit. So keep your piece of paper with you. We're going to solve more of those in a minute here. And you've seen this before in your high school, I bet, but this is a refresher. Tell me, in case of A, is this good precision, bad precision, good accuracy, or bad accuracy? What do you think of A? Oh, no, that you don't have to write that. Sorry, for calculation. Dara? Yes. A is good precision. So your values are all close to each other, but they're away from your target or your true value. So this could be due to something we call systematic error. We'll learn about different types of error. Systematic error could be, well, the pipette is not calibrated correctly. So you're always dispensing, you think you're dispensing one amount, but you're probably dispensing 0.8 amount. So you're always getting consistently wrong data. It could be the balance. It could be you not knowing how to use the pipette accurately, which we will learn next week in lab how to use the mechanical pipette. Okay, so B, what can we say, Zoe, about P?
Good precision and good accuracy.
Absolutely. So now your values are close to each other, and then they are close to target. What do you think about C? Yes, Ashinu? Yeah, you know, you're having a bad day. It's not good. So nothing you're doing here is good. Okay, and how about D? Yes, Mike. Oh, go ahead. Okay, I'm sorry, Michael.
I think that one was.
You know, this, from just eyeballing it, if you take the average of that, it might be close to the value, because you have some are really close. So you might have good accuracy, but your precision is really all over the place in this one. Okay, good. So let's talk about accuracy and how you measure that. So we do measure accuracy by determining the error. And the error, you can determine the absolute error. Okay. And then X with a bar on top is your average, your mean of your replication. You have 5 replication, 3 replication, whatever. Take the average, that's your X with a bar. Minus T. So absolute error, usually it's absolute value. Even if your value is negative, it's absolute value. It's basically just the difference between your average and the true value. T is true value. We get true value. Sometimes I tell you whatever is on the USDA for fat content is your true value. So compare your fat content in your cheddar cheese to that USDA cheddar cheese fat value. So that would be your true value, and that's your mean from analysis. Okay, but To determine really the accuracy, you want to calculate percent relative error. To calculate percent relative error, so it's relative to the true mean. So you take the difference between the average and your true mean over the true mean, and to get percentage, you multiply by 100. So you get your percent relative error. So rule of thumb, anything less than 10% difference, you say this is good accuracy. Anything less than 5% difference or 5% relative error, you say this is excellent accuracy. Okay, so that's kind of where we go with that. All right, let's do more calculations. So you're using your mechanical pipette. You took 3 measurements of 1 ml in terms of weight. And that's what you will be doing in the lab. You're going to take 1 ml using mechanical pipette and measure the weight of the 1 ml. Okay, so determine mean true value. What is your true value in this case? Your 1 ml. I'm telling you, this is a pipette for 1 ml. So that 1 ml is your true value, or if the density of water is 1 at a specific room temperature, then the weight would be 1 gram, which you will convert volume to weight using density and measuring temperature of water in lab next week. Okay, so have fun with some calculations. Let me know when you have any of these values. Yes, Grace.
I have the mean.
Yeah, so what's your mean? 0.9961 is your mean. Very good. If I want to report it by significant value, which we will learn about based on the decimal points you have on your analytical balance. So keep that in mind, because that would help you next week in lab to determine significant value. If my balance reads up to 5 digits after the decimal, the last digit is rounded, is always rounded, then you would report only 4 decimal points. You round the 4th decimal point. If my analytical balance reads to 4 digits, the 4th digit is always rounded in the balance. Then I would report 3 decimal points after the number. Okay, now this is beside the point for now, but keep in mind for next week's lab. All right, we said the true value is 1. What is your absolute error? Yes, Lenny? Negative 0.0039, you can report it as negative, you can report it as absolute. Both ways is correct. It only tells you your deviation that, okay, so my value is lower than the true mean if I have a negative, or my value is higher than the true mean. That's only the direction that it will give you the direction of how different it is. All right, so then relative error, you divide by 1, right? And then percent relative error, you multiply by 100. So there they are for you. Okay, and you can, like I said, report it with a negative or without a negative. It's good either way. So this is accuracy. So let's talk a little bit about precision. So precision, again, we said how close your data points of one sample to each other. Okay, so standard deviation is the first calculation you would do towards precision. And this is an equation you want to learn. It's not hard. You probably learned it before. You just have to remember. In a quiz or an exam, I might give you numbers and I tell me the precision. So you really need to know that equation. And you'll do a lot of that calculation in lab, so this will make it easy to remember. So standard deviation is the square root of the summation. Xi is any of your data points minus the average. So the difference between any data point from the average squared over your degrees of freedom, which basically n minus 1, which is the number of replication minus 1. Okay. So that's your standard deviation. Now, coefficient of variation, you'll see that when I want you to report precision of your data in the lab, I tell you in the table, give me coefficient of variation, not just standard deviation, and I'll show you why. But coefficient of variation is basically your standard of deviation divided by the mean multiplied by 100. So here you are correcting by the size of your mean. Now, I'll show you an example of why this is important to correct for the size of the mean. And again, a rule of thumb, anything less than 10% is good precision. Anything less than 5% is excellent precision, okay? Above 10, I'm just gonna start limping when my student gives me a coefficient of variation of 15%. And I say, on the edge of repeat the experiment. So, yeah, so basically this is important. I'm going to show you something here to tell you, to demonstrate why coefficient of variation is a better representative of precision. Okay, so here you have a flour sample, and we measured protein in this flour using NIR, which is a secondary method of analysis calibrated using official methods of analysis. We'll learn about NIR later. Okay, so I got a value of 12 plus or minus 1.2 standard deviation. Okay, now I have another type of sample that has a much higher protein content. So here, the size of the mean is greater. So I have 92%, and I have a standard deviation more than double. And we got the measurement using a nitrogen-based method, which is DUMAS. You'll learn about it in the proteins chapter. So by looking at this data, can you tell me which method is more precise, the DUMAS or NIR? Okay, let's look to see who's, yeah, go ahead, Diane.
NIR is standard deviation is significantly worse.
So you go with NIR by looking at standard deviation. I'm going to have you hold that thought. Shri? Huh? The second one has a lower CV. So the CV, or the coefficient of variation, is basically your standard deviation divided by the mean multiplied by 100. If we do that, we get about 3% coefficient of variation. If I take the standard deviation here and divide it by the mean, I get about 10% coefficient of variation. So DUMAS is more precise in this case than NIR. But usually NIR has good precision, but this is just a random example. So the random example to show you that, when you have bigger mean, you're gonna have bigger standard deviation. Because it's based on calculation. So you have a bigger mean, you have bigger standard deviation, but when you correct for the size of the mean, then you can actually compare method A to method B when you are looking at different means, different sizes. Now, why is this relevant to you and why is it important? Because when we do the proximate analysis labs, some of you will have flour, some of you will have cheese, some will have almonds. So all are different food products, and we're going to use different methods of analysis for these different products. And I'm going to ask you which of these methods are more precise. So you have so many different means. Standard deviation is not going to be a good measure for you. So you have to measure coefficient of variation so you can decide which method is more precise for which samples. Okay. So the last one here is confidence interval or confidence limit. So usually here is, it's basically telling you where your average lie with respect to the other data points. So the range of your data, where you are confident that the average lies within that range. Okay, so that's why it's called confidence interval. And sometimes you want to go with 95% confidence. Most of the time for biological data, you go with 95. Some forms of data accept 90%. Some forms of data accept 99% confidence. But for us, we'll take 95% confidence. And we use either z-value table or t-value table. So if we have replication less than 25 samples, which usually we do in food analysis, our replication is less than 25. We use t-values for this equation, which is your average plus or minus your standard error. And standard error is t-value times standard deviation over the square root of your number of replication and value. So I will tell you that we have 3 minutes to do this. I will tell you what, so we need a confidence interval at 95% confidence. I'm going to tell you what the t-value here, because you have 3 replications, so it's less than 25. I'm going to use t-value. So I'm going to go to the t-value table. Chapter 4, t-value. I swear there's a t-value in there. Here it is. Okay. So for t, when you look at the t-table, again, you see that in your statistics class. You would normally have a table with different levels of confidence, 95, 99, or 99.9. Sometimes you see 90%. And then degrees of freedom, which is n-1. What's the degrees of freedom here is 2. So in the table, I will look for t-value when I have 2 degrees of freedom and 95% confidence. That would be 4.3. So that's the value you need for the t-value to determine the confidence interval at 95%. All right. What do we have, let's say, for confidence, no, before confidence interval? Coefficient of variation, what did you guys get? It's going to take you a little bit. Okay, I'll wait. We have 1 minute and a half, no pressure. Anybody? Do you have a value plan? Do you have a value?
I have the mean.
You have the mean?
Yeah.
What do you have for me?
4.996.
Yep. Anybody with coefficient of variation already? You? Yeah.
No, I did not.
What do you have, Abby? Coefficient variation? There must be something off with your calculation. Revisit that. Tyler? 0.19. Yes, we rounded to 0.19. Yes, so that's your coefficient of variation. And this is a common mistake, folks. Usually in students divide standard deviation by the mean and forget to multiply by 100. So always multiply by 100. That's a percentage. So it's 0.19%. Anybody has a coefficient of or confidence interval? I blanked for a minute. Confidence interval. Okay, we're running out of time. Do you have anything? No. Okay. Confidence interval, basically, you just apply the equation and you can report it as plus or minus your standard error, which is t times standard deviation over the square root of n. Or you can subtract 0.0048 from this average and add 0.0048 to this average and report it as range. This number and that number. So you can report it as a range, or you can report it as the average plus or minus your standard error. Okay, well, that's it, you guys. Before you leave, bring me your sheet of paper to get your +2, and I will see you on Friday.